Have you ever watched something happening, like a science experiment, and it seems to just fizzle out before it's done? Well, today we're diving into the reason why. It's a huge concept called chemical equilibrium, and trust me, it explains so much about how our world works. Let's get right into it.
All right, let's kick things off with a simple question. When you think about a chemical reaction, what comes to mind? Is it kind of like a one-way street? You put your reactants in, you get your products out, and that's it, story's over.
And yeah, for a lot of things, that totally makes sense, right? Think about lighting a match. Poof, it burns. You get some ash, some smoke. You can't just unburn the match. The whole thing definitely seems to go in one direction and one direction only.
But, and this is the twist that changes everything, that one-way trip is actually the exception. It's not the rule. Turns out most chemical reactions are way more like a busy two-way street, with traffic flowing in both directions at the same time.
So let's tackle this myth head-on. Why is it that thinking of reactions as a simple one-way process is really only giving us half the story of what's actually going on?
The whole secret is this idea of a reversible reaction. And it's pretty much exactly what it sounds like. It means the products, the stuff you make, don't just sit there. They can actually react with each other and change right back into the stuff you started with. It's not a one-way ticket, it's a round trip.
And get this, because this is kind of wild. Our source material points out that pretty much all chemical reactions are reversible if you get the conditions just right. Yeah, even that burned match. Theoretically, you could reverse it. It's just ridiculously, almost impossibly hard to do. This idea that reactions can go backwards is the key to everything else we're going to talk about.
Okay, so if we've got reactions that can go forwards and backwards, what happens when they're both going at the exact same time inside the same container?
Well, that brings us to the star of our show, chemical equilibrium. Now, the most important word on this slide is rate. Equilibrium is not when you have equal amounts of chemicals. No, it's when the speed of the forward reaction perfectly matches the speed of the reverse reaction.
There's this quote from our source text that just nails it. The reactions don't stop. They're both still churning away. But because they're happening at the exact same speed, the overall picture, the amounts of everything, looks like it's frozen. This is what we call a dynamic equilibrium. It's not static, it's dynamic.
To really get this dynamic idea, let's try a little thought experiment. Picture two huge beakers. One is labeled reactants and the other products. We start by putting all the water in the reactants beaker. Now imagine two people start scooping water and pouring it into the other person's beaker at the same time. At first, the person with the full beaker is moving a ton of water, while the other person has nothing to scoop. But pretty soon, as the levels change, the rates start to even out. And eventually, they hit this perfect point where they're transferring the exact same amount of water back and forth with every scoop. The water levels in the big beakers totally stop changing, but are they still scooping? You bet they are. That right there is dynamic equilibrium. So you see, equilibrium isn't this dead, static thing at all. It's this beautiful, active, perfectly balanced dance of molecules. It's a true balancing act that nature is pulling off all the time, all around us. Okay, so if the amounts of chemicals aren't necessarily equal at equilibrium, how in the world do we describe where that balance point actually is? Well, for that, scientists use something called the equilibrium constant, or just K. Now, don't let the name equilibrium constant scare you. Just think of it like a scorecard that tells you the final story of the reaction's balance. So what's this score telling us? Well, it's actually pretty simple. If K is a really small number, it means the balance is way over on the side of the reactants. The reaction basically just gets started, then hits equilibrium almost immediately. But if K is a big number, that means the balance heavily favors the products. The reaction goes almost all the way to the finish line, turning most of its reactants into products before it finally balances out. Okay, that's the theory. But does this K thing, this scorecard, actually hold up in a real lab? Let's take a look at a classic experiment and find out. So, picture this. We've got a sealed glass flask with some hydrogen gas and some iodine gas, and we heat it up. Now, the really cool part about this specific reaction is that the iodine gas has this awesome violet color. This means we can literally watch the reaction happen. As it approaches equilibrium, that bright purple color will fade until it settles into a constant, steady shade. So scientists ran this same experiment 4 separate times. And look at the table. They started with totally different amounts each time. Sometimes more reactants, sometimes they even started with just the product and let it run backwards. They let each one settle down, reach equilibrium, and then they measured the final amounts of everything. And notice, those final concentrations in the middle are all over the place. They're all different. But what happens when we calculate that special K ratio for each one?
Check this out. It's incredible. It doesn't matter what they started with, it doesn't matter what the final amounts were. When you calculate that ratio of products to reactants, you get almost the exact same number every single time, 54.34. This isn't just a coincidence, folks. This is a fundamental law of how nature works.
I mean, how cool is that? It's literally proof in a bottle. This simple, elegant experiment shows us that the whole theory of K isn't just math on a page. It's real, and we can see it happen.
And this is the big takeaway, right here. For any specific reaction at a specific temperature, there is one magic number, K. The individual amounts can be whatever, but the ratio they all settle into is constant. It's the system's fingerprint.
So just remember, when that purple color in the flask stopped changing, it wasn't because everything stopped. Oh no! Inside that flask, the forward reaction, hydrogen and iodine smashing together, is still going strong. And the reverse reaction, hydrogen iodide breaking apart, is also going strong. They're just happening at the exact same perfectly balanced rate. And from the outside, it just looks still. That's the unseen balance.
So when you look at it that way, what might seem like a simple, boring, stable mixture is actually a whirlwind of activity, all held in a perfect, invisible balance.
Equilibrium is nature's default setting. It's the stable place that chemical systems always try to get to. But that powerful balance leaves us with a really fascinating question, right? What happens if you try to mess with it? What if you push it or poke it? If you add more stuff or change the temperature? How does nature's balancing act respond? Well, that's a story for another time.